Thank you, Chairman, for your kind introduction. Good morning, ladies and gentlemen. First, I would like to express my appreciation to the organizers for inviting me to give this plenary talk. And today, I would like to share with you my recent results on the nature and, may I have the hand? Microphone. The result of the nature and the mechanism for the crack initiation for very high cycle fatigue. And my talk will contain 5 parts. The first is introduction, and then the characteristics of crack initiation, and then the nature and the mechanism of crack initiation region, and then to verify our model, and finally the conclusions. First, I would like to mention what is very high cycle fatigue. I think all of us, perhaps all of us, know that the conventional fatigue limits is regarded as the fatigue strength at the loading cycles of 10 to 7. But in recent decades, there are quite a number of research investigations reported that the fatigue failure may happen beyond 10 to 7 cycles of loading. And the related fatigue strength is below the conventional fatigue limits, so this is called very high cycle fatigue. And this brief example showing in this area is very high cycle fatigue. And for very high cycle fatigue, the crack initiation is always from the interior or subsurface of the specimen. And the morphology I will mention in the following slides. And we know that for many engineering structures and components, they all require a large number of more than 10 to 8 cycles of safe loading. So very high cycle fatigue has a very important engineering applications. This is another example showing what happens in the very high cycle fatigue. It shows the crack initiation morphology is a kind of fisheye pattern and also a rough surface of fine granular area. And this tells us that for very high cycle fatigue, the mechanism is different from what we know of low cycle and high cycle fatigue. For that, the crack initiation is always from the surface due to some kind of PSP mechanism. But for very high cycle fatigue, it's from the subsurface or interior of the specimen, so the mechanism is quite different. So in my talk today, first I will show the characteristics of crack initiation for very high cycle fatigue. Then I will try to answer 2 questions. The first question is, what is the nature of crack initiation for very high cycle fatigue? And the second question is, what is the mechanism for the formation of this region? Again, this is an example showing the crack initiation of very high cycle fatigue is from the subsurface of the material. For this case, we see that there's a morphology called fisheye, and in the center is a kind of rough surface called fine granular area, and it's due to an inclusion as crack origin. And for this case, the size of FGA is about 66 microns, and the fisheye is about 206 microns. So now we may have an idea of the size of FGA and fisheye. And we measure a number of specimens to show that the size of FGA is between 40 and 100 microns. And also we calculate the delta K for the crack initiation region, that's delta K FGA, and the results show that this value is quite stable. It's between a range of 4 and 6 megapascal square meter. And then we collect a large number of data from our results and also from literature. And also we put two curves. This is an upper curve, our upper bound of 6 megapascal square meter and a lower bound of 4 pascal square meter. And we may see that almost all the data are within this range. So not just our results, but also the result from literature, so that all of these data within this range, meaning that this value is quite stable. Therefore, we said that this size, the size of GA, is for the crack initiation process, is a kind of intrinsic dimension for crack initiation or very high cycle fatigue. This is our idea, our consideration. And then from this kind of consideration, we are able to calculate the fatigue life consumed in this region during crack initiation. And also we are able to estimate the crack extension rate within this small range. But we just would like to take advantage of two formulas of plastic zone size and also the characteristic size of material. And we assume that the plastic zone size of the crack equals to the plastic zone size of the material, that formation of this crack initiation zone is completed. Under this simple assumption, we may get this, or we come up with this result showing that the value of theta k for SGA is a function, is just a function of shear modulus and Berger's vector of the material. So, and for this equation, we may get the result for steels is 5.5 megapascal square meter. It's quite in good agreement with our previous, or with my previous slides of 4 and 6 megapascal square meter. Then I will show you the results or the estimations of fatigue life and the extension and the crack extension rates within this small range. The idea is that the life for initiation is the life of total number minus n sub 1 and n sub 2. And n sub 1 is from the FGA to boundary of GA to the boundary of fisheye. And n sub 2 is from n sub 2 to the final fracture point. So we may, of course, we have the total number of fatigue life or the loading cycles. And if we can get n sub 1 and n sub 2, and then we can have the life for crack initiation. And we use the formula of Paris relation to obtain n sub 1 and n sub 2. And therefore, we get this result showing that normalized fatigue life due to initiation as a function of number cycles to failure. And the important thing is that it tells us for the range or the regime of very high cycle fatigue, the normalized fatigue life is larger than 95%. It means that for this kind of fatigue process, this kind of fatigue failure, the majority part of fatigue life is consumed due to crack initiation. And also we estimate, I called extension rate or crack extension rate within this small range of crack initiation. The value is 10 to minus 12 and 10 to minus 13 meter per cycle. Is very, very slow. So I just summarize the previous slides for very high cycle fatigue of high-strength steel. First is that crack is initiated from the interior material, and second is the homology is fisheye and FGA patterns, and also that data or the value of delta K is stable and is a function of Burgers vector and shear modulus of material. And also the fatigue life is consumed, or a large part of fatigue life is consumed by the crack initiation process. And finally, we said that FGA, the crack initiation region, is the characteristic region for crack initiation for very high cycle fatigue. So now we have an idea that the initiation process is so important. Therefore, we ask these two questions. The first, what is the nature of FGA? The second question is, what is the mechanism of this region formation? But before I describe our results, I would like just briefly mention some previous models. The first one is hydrogen-assisted crack growth to form FGA region. The basic consideration is that this type of rough surface is due to the existence of hydrogen inside the material. And this kind of interaction between the hydrogen and the material that defects or damage process will cause a type of rough surface during the fracture process. And the second model is called the cohesion of spherical carbides to form the region of FGA. The basic consideration is that because there's an existence of spherical carbides in the steels, for example, and that the bonding or the cohesion between the carbides and the material will cause the formation of rough surface during the fracture process. And the third model is called formation and debonding of fine granular layer. The main consideration is that during the cracking process, or before the crack growth, there will be a kind of plastic deformation to cause the formation of fine granular layer. And during the cracking process, there will be a debonding between a fine granular layer and the matrix, and therefore to cause the morphology of rough surface. And also there are a couple of additional models similar to this debonding of fine granular area to form this kind of rough surface. But this type of models cannot explain some experimental observations. I will show you some cases. This one, we may see that it's a kind of medium carbon steel. We may see a morphology of fisheye pattern, but there's a kind of very clear initiation region without the morphology of so-called FGA. And the second case is also from a kind of medium carbon steel. And we also may see the morphology of fisheye, but without FGA pattern. And the third one is very interesting that for the case of loading after 60 million loading cycles, there's a FGA morphology, but with the for the case of relatively small number of loading cycles, there's without FGA morphology. And the fourth one showing that for -1 stress ratio is a morphology with a morphology of fisheye and FGA. But for a stress ratio of 0.5, there's a initiation region without rough surface of FGA. So such cases cannot be well explained by existing models. Therefore, we try to reveal what is the real nature of this very important region to consume so large part of fatigue life. And we use ordinary rotating bending method, and the stress ratio is -1, and use a high strength steel for this testing. And this action data, and we choose 2 specimens for detailed observations. It's the green one and red one. And for the red one, it failed in a very high cycle fatigue regime. And there's a top view from the low magnification to high magnification to show a rough surface during the crack initiation process. And then we use the method of ion beam polishing there to get a kind of profile sample. And we observe this this initiation region to see there's a kind of layer about 650 nanometers of rough surface. And then we further use the technique of FIP, focus ion beam cutting, to cut the specimen in the location of crack initiation region, and the TM image shows that underneath the fracture surface is the region of FGA as a kind of fine microstructure, and inside the fracture surface is a kind of coarse microstructure. And we also use the SAD as a selected area diffraction, and the size of SAD is 200 nanometers. And we saw that for the location of FGA region is a kind of discontinuous circles. But inside the specimen is a kind of isolated spots, meaning that this area is a kind of coarse microstructure and is fine structure, meaning that a number of grains inside this small area, 200 nanometers. And this is another result showing that in the region of FGA area, the diffraction is a discontinuous circle, discontinuous circles, and our measurement shows that the grain size is 48. The average size is 48 nanometers. And then we observe another specimen. That's the green specimen, and we we use the both fracture surfaces. This is the negative part and positive part of fracture surfaces, and we cut the fit sample from almost the same location. We just try to see how about the morphology on the both sides of the specimen. And okay, this negative and this positive fracture surfaces, we see that in the FGA location is discontinuous circles, and outside, we cut the fit sample is just between or across the boundary of fisheye and FGA. So the fit sample, a part of fit sample is FGA region, and another part is fisheye outside FGA. And this shows that in the part outside FGA is almost isolated spots. So only for the region of FGA is a kind of fine microstructure. And this also is in the area of FGA is it is discontinuous circles. So I will say that our observations shows that the region of FGA is a kind of microstructure. In fact, it's a kind of nanograin layer. But beyond this region is called microstructure, or underneath or outside this region is also called microstructure. Therefore, we propose this kind of model called numerous cyclic pressing, NCP. It says that first, crack will perhaps it will form by the debonding of inclusion and matrix. Of course, there's a kind of plastic, localized plastic deformation. And then after the formation of the crack, there will be a kind of contacting between the crack surfaces. And this type of contacting will be associated by the crack closure effect and also the relaxation of residual stress. And this process, again, after million cycles of loading. So this is the main concept of our consideration of model. Due to this kind of contacting between the originated crack and also the crack surfaces to produce such kind of micro or such kind of narrow grain layer. Perhaps some of you know that there's a concept of sphere plastic deformation to produce fine or nanograins. And we think that this type of crack initiation is similar to that type of process to produce fine or nano-sized grains. Okay, now we will try to verify our proposed model. To verify this, we may have two predictions. For the first prediction is because this process is due to the contacting of the crack surfaces, so we may predict that for the positive stress ratio, there will be less action of crack closure effect. So this kind of nanograin layer on fracture surfaces will be less possible. And the second prediction is that even for negative stress ratio, for example, -1 stress ratio, if the loading cycles is not enough, is not sufficient, this type of surface, this type of fracture surface with fine microstructures will also be less possible. Then we carry out another group of experiments, and this time we use the method of ultrasonic fatigue testing, and also a high strength steel, and the stress ratio is -1, -0.5, and 0.1 and 0.3. And this is the facility as an ultrasonic machine equipped with an ordinary tensile machine. And we select 5 specimens for observation, the blue one, the orangey one, and red, pink, and green one. This is low loading cycles, and the 4 others are within very high cycle fatigue regime. And perhaps I have had to rush, right? It's almost the time. So I just would like to show you the result of this. This is the -1 stress ratio with relatively low loading cycles. And we see that it's a kind of slightly elongated deflection pattern. It's a kind of texture microstructure, meaning that within this small range of, or small area of SAD, just perhaps a couple of grains. And for minus 0.5, it's also elongated diffraction. But for 0.1 and 0.3, stretch ratio is just underneath that fracture, that crack initiation region is isolated spots. So these observations verify the first prediction, and these verify the second prediction. And now I conclude my talk. The first is that the region of FGA is very interesting and important, and the size is between 40 and 100 microns. Is an intrinsic characteristic dimension for very high cycle fatigue. And the crack initiation life is larger than 95% for very high cycle fatigue. And the nature of FGA is a layer of nanograms, and it is about 500 and 800 nanometers on both surfaces. And the size is about 50 nanometers. And the mechanism of FGA formation is due to the numerous cyclic pressing induced grain refinement at crack tip. And this model may provide an insight for understanding the crack initiation process for very high cycle fatigue. And also this kind of concept is possible to tell us for creating a new approach to produce material thin film with nano-sized grains. I think that's all of my presentation. Thank you very much.
Thank you, Professor Hong. The paper is open for some questions. Are there any questions? In the meanwhile, there is some possible seats here. People standing on the back can move after the question, please.
Hello, Volkanus, Airbus Operations GmbH. As far as I understand, it sounds like a material property, the initiation of the very high cycle fatigue. Cannot we optimize the microstructure for delay of the fatigue to extend the life of the structure? Or what do you recommend? I mean,
sorry, I'm not quite catch your question. Can you repeat again?
The microstructure, which may, what do you recommend? What kind of microstructure can help against this very high cycle fatigue initiation?
Okay.
My understanding is it's something like material.
Thank you. Thank you for your question. I think very high cycle fatigue is sensitive to high strength materials. And for some low strength materials, there's a kind of low sensitive behavior. So if I just would like to say, if we use some kind of high strength steel, we have to care about this. It must be a possibility of very high cycle fatigue failure. For example, in the previous investigation, we noticed that, for example, for some kind of steel, carbon steel or low alloy steels, if the tensile strength is lower than 1,300 megapascal, for example, the very high cycle fatigue sensitivity is very low. So, to answer your question, though the microstructure with low strength will have low possibility of very high cycle fatigue behavior. Does that answer your question?
More or less, you say only very high strength steel is actually acceptable. but I remember something like you saw some figure at which aluminum is also. There is a characteristic delta K threshold also for aluminum, I think.
Yes.
And also at Airbus, we have acoustic fatigue in our aluminum structure. Is a mechanism different? Or?
You know, recently we also did an experiment from titanium alloy, but not alloy, not aluminum alloy. We got the results very similar to what I mentioned in this talk. There's a kind of fine microstructure at the initiation region. But for aluminum alloys, so far the results are not available. I mean, for this kind of very detailed observations on the crack initiation region. But for you are right. I saw the result of the equation delta K as a function of shear modulus and Berg's vector to show the delta K FGF for aluminum alloy is about 1.9 megapascal square meter, something like that. And this result is also very similar to the experimental data.
Okay, thank you very much, Professor Hong again.
Okay. Thank you very much.